So, a very big welcome to Denby Dale Amateur Radio Club and our online meetings and online speakers. And I'm delighted tonight. We've got Frank K4FMH, who in the last couple of years has spoken at Denby Dale a couple of times on different subjects. So, a pleasure to have you back again, Frank. In the meantime, Radio Society of Great Britain members, RSGB members, will have noticed in July and August there was a two-part feature by Frank K4FMH and Scott McIntosh on Solar Cycle 25. So I'm not going to steal Frank's piece here in talking about that piece, other than to say, as radio amateurs, those of us in this room here who use HF, aren't we waiting with bated breath for Solar Cycle 25? Solar Cycle 24 was one of the more depressing aspects of radio propagation, wasn't it? And even on its maximum, nothing very exciting occurred. And when we were down in the solar minimum, didn't we know we were in the solar minimum? So we're all very much looking forward to this. And in terms of us as amateurs, we've already had a few glimpses over the last 2 or 3 months of propagation inspired by the increased sun activity. So, Frank, I'm going to hand the microphone over to you and let you take it forward from there.
Thank you very much, Nick, and everyone. I'll try to share my screen. If I want to make sure that I share sound with that, share sound, because I have a one little video. Now, can everybody see my PowerPoint?
We can.
Slide? Is my audio okay? You're getting my microphone.
Your microphone audio is absolutely brilliant, Frank.
Great. Thank you. Thank you so much. Listen, I'm extremely honored to be asked back once again to speak to Denby Dale. I think our time is ultimately our most precious commodity. And as we get older, I think I'd get higher agreement with that. And as someone who is in his late 60s, I'm 69. I hope not, but this might be my last sunspot cycle. So when you put it in those terms, for your choice to spend some time listening to me nattering about with this is quite an honor. I had the pleasure of interviewing Dr. Scott McIntosh of the National Center for Atmospheric Research in Colorado. He's a native of Scotland. And in 2020 for the ICQ Podcast, he and I hit it off both professionally and personally. We've become close friends. So the talk tonight is revolutionary alternatives in sunspot prediction. And it's just based on this SGP RadCom two-part article. I want to say at the outset and wave my arms, Dr. McIntosh is a solar physicist, and I'm not. My PhD is in sociology and statistics with a minor in computer science. I'm a statistician and philosopher of science, taught those courses to PhD students and faculty, been a consultant and all that good stuff. And I've worked with Scott since 2020 to learn more about his team's work. In fact, we were online this morning, and he's having a problem, getting reviewers to agree to a paper they're trying to publish. I'll show you one slide out of that very paper before it actually gets published. It will, I'm certain. But the meat and potatoes of the work is from Scott and his team. My contributions were to help put a bow on it, if you will, but to place their struggle about publishing a new theory and a model of sunspot predictions in peer-reviewed journals. Now, I don't know, I published 50 or more peer-reviewed articles, 100 total publications, and several books. I've been editor-in-chief for Springer Media, a very large scientific publisher. So I've kind of been on both sides of the desk. So I'm happy to give Scott and his team, Bob Lehman in Maryland and others, advice on how to hoist reviewers on their own petard, so to speak. They may have a standard for your article that they didn't follow in things they published, some of those things. And I've also lent a hand, if you will, with some of the statistical basis of their talk. If seeing the covers helped bring any bells, I was very honored that Elaine chose our article to be the cover story on July. We finished off with the actual predictions for cycle 25 in August. And on the right, you'll see just a few bullet points about my talk. I want to apologize to you. This is not a zero-sum talk. Hey, I put these two wires together and plugged it in and it worked. Isn't it great? No, it's a lot more nuanced than that. I want to apologize. It's going to run about 45 minutes. So I'll try to get with it and stay on course. But I hope you'll stay with me, because if you're interested particularly in HF, then this is all new stuff. This is unfolding literally as I'm speaking, as Scott and his team publish their next paper. So I want to begin at the beginning, our present day sunspot cycle. What are the occurrences? What are the predictions for cycle 25 and the competing predictions? If you'll kind of feast your eyes on this black little snake of the smooth sunspot counts, these are actually observed counts. Notice that the green lines are the monthlies, and then there's a little tan line that's estimated daily. I want to say something up front. We get blinded by the smooth sunspot numbers. A smooth sunspot never affected our propagation. I'm going to say that again. A smooth sunspot never influenced our propagation. Case in point, my friend Pete Giuliano on the Solar Smoke podcast, he said, "Oh, Frank, that cycle 25 stuff of Macintosh is crap. The bands are bollocks." And I said, "Well, why?" She said, "Well, the sunspot number is so-and-so, and there's nothing going on." And I pointed out to him, look, you see, you might be at a 65, say, on smooth. Well, look at within a day what you had. If my cursor will find, you could have had an actual sunspot up over 140, or more likely in his case, you could have had one that was near zero. But the smooth was in the middle. The smooth is an average over a time period for us humans. It's not about nature. Just want to point that out as we progress here. The two blue lines are the NASA NOAA official projections. When they came out, it was going to be a ho-hum, another repeat of the previous cycle, and that's the light blue one. They made an adjustment after Macintosh and his team released their predictions. They shifted at 6 months starting, and then there was a little better. But these two are the official, what we worship at the Holy Church of NOAA and NASA. That's what their numbers are. The dark green one is simply if we take the average since 1750 and plot it out over time, it's going to be this. So their predictions were substantially lower. Do some quick math, about 175 to at least 75 lower at 2025. Well, when Scott and his team released their predictions, as they say, all bloody hell broke loose, because suddenly it was in a night and day sort of forecast. The question is, who's right? And I want to explore that. So we tend to look at sunspot cycles as a very key thing. And my punchline here is that we have a loyalty to a paradigm in the face of many anomalies. In the US, we have the Dow Jones Industrial Index of certain stocks that is tracked, and it's kind of what we look at. If you just bet the Dow Jones, you have something similar in Britain and in Europe and in other countries. Japan is the Nikkei and others. So the sunspot propagation indices or propagation indices in general, which the sunspots are a key one, they're much like the Dow Jones Index is for economists and financial advisors. On the right side of the screen, we've got this famous web widget of solar terrestrial data. It's ubiquitous. I think I've even got it on my K4FMH.com site. We examined this, those of us who are interested in particularly HF propagation, every day. We look at it in detail, and it offers the latest data. So forecasting the sunspot number has been the chief element of concern since the earliest ARL handbooks from about 1940 on, and related books by writers such as your own Steve Nichols in the UK. The US writer Eric Nichols. If you say propagation and Nichols, sometimes people get these confused. And then the person that the ARL goes to, Carl Schwabe. And Carl is certainly one of the most knowledgeable thinkers and writers in propagation here, at least on this side of the pond, a retired engineer. Tomas Hood, who writes in CQ magazine. I don't think he's published a book, but he writes a very important column here. So what's our focus? Our focus is on looking at the amplitude, that is the peak and the trough, as well as when one of those phases goes from one to the other, the transition from one cycle to another. Well, in the United States, you probably have something similar in England and United Kingdom. We have some of what reading specialists call basal readers. It's not about the story. It's about just learning basic words and how to put them together. The Dick and Jane series of children's books here in the U.S., Dick and Jane, they have a dog named Spot. They also have a cat named Puff. And the famous lines of there is see Spot, run. Well, we tend to operate that way. There's no thinking involved. See sunspot's curve. So we tend to kind of dwell on that as a given. It's effectively a cottage industry in our hobby about people predicting what's going to happen with sunspots. Now, whether it's an amateur radio or astrophysics, practitioners tend to follow this canonical dictum of a sine wave cycle of about 11 years from peak to peak. And this has been the case ever since Heinrich Schwabe made the initial observations back in the middle of the 1800s. We'll visit Heinrich here in a moment. So the amateur community's prognosticators vary widely in their sophistication. Carl Schwabe has done everything from basic time series modeling, which is a bit of my background, curve fitting techniques. Engineers love to fit curves. I like to say I taught engineers for many years. They'd come take my statistics classes and they learned fast Fourier transforms and they never got over it. Give a small boy a hammer, everything is a nail. Well, engineers tend to want to do curve fitting. Why? Because they learn to do that in their core discipline. Now, on the other end, we have some amateur radio practitioners that may just take the last cycle, photocopy it, if you will, and put it over, on the graph and say, well, this is my rough estimate of cycle 25. I'm going to look at that in the next slide. Here's the key thing. My mentor in forecasting is Robert Goodrich, now passed on. He was the leading consultant for the electric power industry in the United States. We can all appreciate, especially today with climate change and power outages, how really important it is to have accurate forecast about the demand from the grid. So I learned time series modeling from Bob Goodrich. And one of the things that he always said, understand which side of the house you want to live in. Do you simply want to have a prediction model where you don't care why? Or do you want to have an explanatory model where you have a theory of what predicts what and how that occurs? None of the amateur radio prognosticators for sunspots do anything other than a sheer prediction model. No theory about explaining how sunspots change. Real good example of that. Nathan W1YW posted his cycle 25 prediction on QRZ in February 2020. That was all the rage. What do you think is going to happen? And he literally was mimicking, as he said, cycle 24 and then quoting from the NASA NOAA predictions when they came out. Literally took a photocopy of what I like to call the Cookie Monster diagram. That's some I'm sorry to get so technically deep here, but the Cookie Monster, and copied it and placed it here, put it on here, and you are here. So that's a rough estimate of what we're going to expect. And he's given all these projections about when what band will be doing whatever. Don't plan a 24-hour-a-day worldwide prop on 10 meters in 2024. Well, I'm here to tell you that if you looked at Whisper today, 10 meters was open worldwide. Now, we're 2 years prior to that. We'll see what happens in 2024. I want to underscore something. This is not about how smart you are, how educated you are, how bright you are. Nathan is a smart person. He has a PhD. I don't know if it's in astrophysics or if it's in math. He's taught math, I know, from his website. And he's got patents on fractal antennas. I think I read on QRZ, he just got another patent. He's a smart guy. It has nothing to do with that, but it's what it's got to do with our example of ritualistically parroting an existing paradigm without a theory. So let's go through this. What do we say to ourselves? What are our big publications that when we have new people, maybe that come into your club, you say, well, go read the RSGB handbook. If you're in the States, go read the ARL handbook or read these books that they're experts. In the ARL handbook in 2019, since the earliest days, our traditional measure of solar activity has been a basic count of sunspots. In hundreds of years, we've learned the average number goes up and down in a sine wave cycle approximating 11 years. And there's a direct correlation between sunspot activity and ionization. I think no one who understands propagation physics disputes that there's a direct causal connection between sunspot activity and ionization. I watched an old black and white video of an MIT professor on YouTube where he had a plastic tube of nitrogen and he entered some low wave AC current and it lit up like a fluorescent bulb. That's not what's in fluorescent bulb, but it lit up like that because his point was, as you get up in our atmosphere, it's 86% nitrogen. So if AC waves, i.e. RF, get them, look at the ionization. So look at what the sun does to them. No one disputes that. What we don't read here, what causes sunspots? Only the effects of them. Eric Nichols, the US writer, propagation's an art form. We've been getting better. It's far from a hard science. We can't predict when or how many sunspots may pop up at any time. And we're still not sure where we are. Top experts can't agree whether it's going to be the best or worst in the history of ham radio or in the history of man. How typically American with all the hyperbole. Now we'll go across the pond to your neck of the woods and we'll listen to what Steve Nichols has to say. A lot more straightforward. A number of factors have become obvious. The cycles are by no means regular. Average cycle length, about 10.9 years. It varies from 7 to 17 over history. Think about that for a minute. The variation from the shortest cycle to the longest cycle has been almost the length of a cycle itself, about 10 years. So the maximum sunspot activity varies from 49 to 200 with an average of just over 100. The minimum can be anywhere between 0 and 12. So Steve Nichols, in that what I would see is a fairly straightforward British style, kind of focuses a little more on the facts and our observations and less on the hyperbole. Let's look at what Carl Schwabe has to say. My friend Carl, K9LA, I admire him very much, a very good thinker. He's a very objective thinker in his science and engineering. An observation is that we appear to be headed for another long-term period of low solar activity. Although what cycle 25 will do is debated, I think scientists will have a single consensus for cycle 25, low followed by more low ones. Of course, the history of the sun may not be a good predictor of future activity. Okay. Not sure that hangs with previous sentences, but we'll go with that. Not only do we not fully understand the solar cycle process, we only have a couple of hundred years of data for a process that has been going on for thousands or millions of years and is a small sample size indeed. So the upshot of what Carl is saying here is one problem we have and why we can't predict it very well is we only have a couple of hundred of years. What if we had a couple of thousand of years? What if we had a couple of million years? We could just model it, and we would just get a really good model. That assumes that the solar cycle causes itself. Going to come back to that. It assumes that at least in part. Now, all propagation experts in amateur radio make use of this paradigm. I haven't found a single one that doesn't. It's a sine wave amplitude over an 11-year period, and it will rigidly follow that as it supposedly has for millennia. Carl makes that point. This has been accepted canon for almost a century or more. But as Eric Nichols says, top experts can't identify peak, trough, or timing of one cycle to another. So my point is a devotion to a theoretically unexplained 11-year sine wave function as our paradigm for sunspots in the face of all these anomalies is at face value very puzzling. If you're a Star Trek fan, Mr. Spock would say that is not logical. So there's a couple of things about this. It's important for us to understand why we amateurs look at it that way. If you look at sunspots as being what the counts are, this is what we call scientific teleology, that some phenomena is what the measurements are. I'm sure you've heard people debate what is human intelligence, and how often have you heard the answer? Well, IQ is what IQ tests measure. Okay. Some phenomenon, it has a purpose, and that is its cause. Immanuel Kant back in the 1700s, Stuart Nagel in 2012, and more earlier than that, and Barrow and Tipler all identified this scientific teleology. To put it in language that we blokes in a pub might understand, we have the problem of bass awkwardness when we take that approach. But it's really not our fault. We're not solar physicists. We don't do solar physics. Now, Tabitha Scove is a ham who is a solar physicist. You have to take some people like that as exceptions. They are solar physicists. But the rank and file amateurs, Carl Lucius Schwabe, Steve Nichols, Eric Nichols, all these writers, we're not solar physicists. We're ham radio operators. We are just following along. It begins in solar physics itself. Let's see why this is so. And I want to return to some first principles to figure this out. Here's a little video. Nick, if you don't hear the audio, wave your arms and I'll make sure we can. Very short video.
At Kitt Peak Observatory in Arizona, solar astronomer Matt Penn studies this solar surface to discover how photons of light get trapped.
There's a bunch of cirrus today, but hopefully we'll get some data.
Using the McNath-Pierce telescope, he focuses the sun's light to scan the photosphere in detail.
So what we've got are a few small sunspots on the disk of the sun. We've got two sunspots, two large ones. They're heading off to the edge of the sun, to the limb of the sun, but they're all accompanied by smaller sunspots, groups of smaller ones following them.
Sunspots mark areas where light is trapped.
So a sunspot forms a dark spot by removing energy from that part of the sun. It's blocking the convective flows that transport the heat and the light from inside the sun to space, and so what we see then is a cooler region that appears dark to us.
A powerful force stops our photon dead in its tracks, preventing its light and energy from leaving the sun's surface. That force is magnetism. Sunspots take shape where intense magnetism from deep inside the sun blasts up through the photosphere.
The magnetic fields are so strong that it actually stops the convective motion of hot inner material from flowing to the surface. So you actually get what looks like a cool spot on the surface of the sun.
They can be huge, the largest over 10 times the size of Earth.
Okay, so you heard something there that will prove critical, and that is magnetism. I want to show you one more little video. It doesn't have any audio, but I want you to focus on this part of the sun and look at what happens when a filament is expelled from the sun. Boom. It gets sucked back immediately. Now play it again and you'll see that some of the filaments that were smaller, they were able to escape the magnetic influence. See, some of these escape the magnetic influence of the sun, but not that filament. Why is that? Well, like electricity, magnetism has opposing poles. We tend to work with electricity more than magnetism these days, although we, in the early days of amateur radio, we use magnetism more than we do now. So we can think of the sun as being a dynamo internally. That's one of the major paradigms, the dominant thinking about how the sun operates. You know, it's unfortunate. Your mom may have said, don't stick your head in the oven just because your friend did. I think some solar physicists would stick their head in the sun if they could just get away with it, because we don't really know for empirical fact what's going on. So this will be important for us to later on understanding what shapes or causes sunspots and some of their behavior. If you remember some of the movie The Graduate, maybe the late 60s, and Dustin Hoffman, the American actor, was the key role there. And someone whispered to him at a graduation party some career advice, and they whispered into his ear, plastics, go into plastics. Well, the message of this video and what I'm saying is magnets, go into magnets. Now, I want to give you an example. These are two neodymium earth magnets, little disc. I buy them to mount equipment on metal IT plates a lot. Now, I've got these two. They're just little disc, and it's difficult for me to push these together because I've got them in opposing poles. But what happens if I turn them around? Now, gosh, these little, even though these are strong earth magnets, what is the order of magnitude difference between just that I showed you and that you can do at home and that we all learned in elementary school or grade school about how magnets work? Is the order of magnitude 1,000,000 or 1,000,000,000 times in the sun? Gosh, I don't know. Paul Charbonneau, the Canadian, has a great article here, Living Reviews in Solar Physics, Volume 2. And I'll make this available to Nick, my slides, so you don't have to write this down. If you want to go look more at that. Well, I wanted to give that sort of basics, that magnetism is a fundamental way of understanding sunspots. That's what causes sunspots. But the earth of the sun's behavior with magnetism is what's been more of a mystery until now. So how did sunspot behavior become a cycle? And it's what I call the Schwabe inductive inference. Now, here's a picture of Heinrich Schwabe. Now, Galileo supposedly recorded some sunspots, but it's credited to Heinrich Schwabe, born in 1789, died in 1875, for the first compilation of daily sunspots and for the sine wave characterization. He was dedicated. I found this out from doing a lot of reading about him and the period. He was a pharmacist, family business. Why did he do that? So he'd have time to do this. Many scientists of the day didn't get paid to be scientists. We didn't have science as a social institution. Those of the church, the clergy, were often some of the early scientists, even though by today's religious standards, you might find that shocking. We used to keep logbooks. The FCC used to make us in the U.S. maintain a logbook. So we're used to doing that in ham radio. Imagine this. In his logbook of sunspot activities, I read that he noted in one entry, the sunspots were thus and so, and I'll show you those in the next slide. The wall clock had stopped. And oh, by the way, his wife passed away at 9 o'clock. Now, whether that's good or bad for his dedication or not, it's an indication that certainly he was dedicated. So beginning in 1826, and every clear day, he'd scan the sun, record his spots. After 17 years, would you wait 17 years before you found something? Did I say he was dedicated? He said, there's a regular pattern here. And he began noticing that and looking at it, that over a 10-year cycle, not 11, 10-year cycle. And he published this in a paper called Solar Observations during 1843. Nobody much paid any attention. But the periodicity of sunspots is now fully recognized and accepted. And Schwabe is thus credited with one of the most important discoveries in astronomy. Now, over here on the right is a disk that he used to record sunspots. You'll see that 70 means something. These little dots are here, and he had his own little way of making notes. As if you're a physicist or a chemist or a biologist, you learn as a student the importance of the lab notebook, writing down things. Electrical engineers learned that as well. Yet he didn't quite keep everything in a way that we could follow it, some 100 years later, maybe. But he had no doubt that the characterization of periods of 10 years, and these are some of the counts from some of his work. So here's a little histogram, and you begin to see this sine wave emerging. David Hathaway, who worked with NASA over in Huntsville, Alabama, wrote a very nice article about this. And this led to an inductive inference about one of the sun's most systematic behaviors. There was no theory to go with that. He didn't have a theory and then go compile data to test it. That would be a deductive inference. It was an inductive inference. We'll come back to this in a minute. Now, the Swiss astronomer Rudolf Wolf read his paper and was impressed to the point where he spent more than 40 years digging up the archives in astronomy observatories. Now, think about that. Would you read some obscure paper that nobody was paying attention to and dedicate part of your life for the next 45 years or 40 years compiling it? I don't know if I would or not. Well, this led him to set the cycle at 11 years rather than 10. Now, to a statistician, this is not surprising. If you've got a long run of data and you focus only on one part of it, what you may observe there won't necessarily generalize out. So Schwabe said 10. Wolf came up with 11 when you look at it in a longer period. So let's take stock for a second. Here's a plot of the sunspots since about 1750, going back to all of Wolf's data with the NASA projections out here. We can ignore those for a second. Here are the smooth values, and you can kind of see some things in the lower panel that you can't see in the upper one. Well, here's some general observations. If you see something that I don't mention, I'd love to hear from you about them. There's a regular movement up to a peak period and then back down. So sine wave, yeah, that's there, no question. But the peaks aren't consistent. Notice that there are no two of them. Maybe this one and this one are the closest, but gee, they're not next to one another. This one and this one are close. Well, these two might be the closest, but they're the closest to being next to it. They are next to one another. Cycles don't wholly replicate themselves. The previous cycle isn't shaped like the one coming after it. Don't we think things in the past cause things in the future, not things in the future causing things in the past? Okay. So there are irregular gaps, like look at these little skinny valleys. Wow, that's big. That's really big. That's big again. And then we get into some skinnier ones. So if you look at all these little gaps at the bottom, the trough, they vary a great deal. So here's the question. Does it make sense to assume that sunspot cycles are only caused by previous cycle behavior? Isn't there something missing in the characteristics that we can all observe is I've tried to lay them out here in everything we know about the number and the timing of sunspot cycles. Well, the Macintosh team, and I certainly agree, no, it doesn't make sense that sunspot cycles totally and wholly cause themselves. Okay, well then, what about these official predictions? Where do they come from? And my punchline is that it's only a translucent view by the public into how the scientific sausage is made. I'll explain that. Now, in the minima or the depths of the last 3 solar cycles, NASA and NOAA in the US have convened panels of experts. They're experts in solar physics, they're experts in time series analysis, and other associated areas. They are impaneled to assess and forecast the conditions of the upcoming solar maximum. Well, it may be surprising to hear that the panel that does this, they don't tell you how they did it. They don't reveal any detailed documentation of their methods. The only thing they reveal will be in a following slide. So we can't replicate what they did. Now, as Eric Nichols said, good science is subject to peer review. And I think every scientist would agree with that, yet they don't cast their pearls upon us swine out here in the public so we can see. So they release data points that represent their forecast, but not the detailed methods used in creating those numbers. Well, here are a couple of graphs. Now, I mentioned Rudolph Wolf. He had a conjecture about one way of counting sunspots versus another, Schwabe's way or his way. So we often have 2 series of sunspots. And here's the NASA NOAA panel with the version 1 sunspot data and version 2. And you've got models, and I use that loosely, and the citation for Upton and all is in the RadCom article. By the way, if you don't get RadCom, contact me offline. I'll see if I can't make a PDF available to you. I think Elaine would be okay with that. Now, these were models based on climatology, about a dozen, dynamo theory of the sun, about 4, machine learning and neural networks. Oh, machine learning, it's the cool thing. Put that in your grant proposal, it'll get funded. Unfortunately, that's true. Buzzwords do matter there, having been on review panels and having been in charge of review panels. Precursor models, spectral statistical models, surface flux transport, and that's going to have more meaning a little later, and other. So they just tell you, we got these 61 different predictions. We met in a room. Here's what those different predictions look like. The average peak would be about 112 or 119, depending on which data you use. The average of all of them will be 86 or 119. And here's how they vary. Well, to be fair, now the panel has a challenge to use state-of-the-art knowledge to develop a consensus estimate, not a model. So to be fair to them, they're not asked to provide a model, but to come up with a consensus estimate of the sunspot cycle maximum amplitude and when it will happen, that is the transition. They've not had a great deal of success over the last 3 sunspot cycles. Okay, 11 times 3 is about 33. They've been at this not quite 40 years. But it's important to note that they construct their official numerical forecast through a democratic vote of the panel. Now, I want to tell you, there are places for this. Here in the States, we've had this big debate as to whether we're in an economic recession. There's no one model that says we are or we aren't. The National Bureau of Economic Research has expert economists. They meet and they actually make a consensus estimate. We're in a recession. We're not in a recession. That's an expert judgment. There are places for this. Now, in Science magazine, the science writer Sandra Scholes noted 2 significant elements of the panel's discussion. One, she quotes Rachel Howell, the University of Birmingham in the UK, who's a statistician, said, well, there's not a lot of physics involved. And unfortunately, there's not a lot of statistical sophistication involved either. So the chair of that panel, Dr. Bisecker, concedes the point. Well, but we hadn't really found a model that seems to work, and we've been doing it for hundreds of years. Yet, when the panel came out with their final vote, he said, a consensus among experts can often be a better prediction of the future state of a system than a set of the individual predictions. That happens. If you follow hurricane models, in the UK, there is a UK model. In the US, there's a US model. And we often see these in what we call spaghetti models. That is, you got a bunch of wiggly lines that make different assumptions about where a given hurricane is going to go. Often, averaging all those lines is one method of seeing one projection. It generally doesn't tell us where it's going to go, but it is a legitimate method. We don't know how the scientific sausage is made, except it's a democratic vote. Now, I think part of this is the image that, for hams at least, part of the reason that hams tend to worship at the Holy Grail of the official estimates is this. We have this image of NASA, who put somebody on the moon. NOAA, they track all kinds of storms. Now, I worked for NASA under contract in the late 1990s. I was a badged official at the Stennis Space Center, where their commercial remote sensing program is headquartered. I coordinated a $60 million program there. I'm a certified NOAA storm spotter. Some of you may be certified in storm spotting where you are. Both NASA and NOAA do have major supercomputing capabilities. I've seen some of NASA's. We have this image of them, and we think, gosh, they have this great model that predicts sunspots. And one message here is it's just not so. NOAA got an appropriation to buy a pair of 12 petaflop General Dynamics systems that cost $500 million. I work with our congressional delegation and sometimes get asked what I think about certain appropriations, because the joke in Congress was they want a pair of those GD computer systems. So I'll let you figure out what that stood for. Now, here's a picture of the Pleiades supercomputer built by Silicon Graphics at NASA Ames in Mountain View, California. Very impressive. I've used some of these computers. They do have that capacity. But in contrast to our general image that we have about NASA and NOAA, they don't use that. So this sort of reputational vote that they take on a predicted cycle, it's imperative that we understand what we're given and the basis upon which it's rendered. It's not the NASA NOAA supercomputing group that does it. Okay, well then, gosh, how is it that we can have different projections or predictions, and how does that work in science? This is not unusual. The idea of scientific paradigms, how do they work, and what leads them to changing paradigms? Now, there's a tendency for an area of science to stay with an idea or set of ideas, a paradigm, even in the face of it not working very well. Thomas Kuhn, a physicist, published an important book back in 1962 on the structure of scientific revolutions. He defined a paradigm as the broadest unit of understanding in a field of science. This is also not pie in the sky, but very practical. I've worked with different federal agencies to use Kuhn's model of science to see whether or not they are systematically rejecting new and fundamentally different ideas, because who is making judgments on the review panels? It's people who get money and are funded to do work in the existing paradigm. So here's a model on the next page. Don't let it frighten you. It's quite complicated, but we'll walk through it so you can get a sense of the rhythm of how these things change. In the middle here, we have a wheel, and it starts with an input: pre-science, normal science, anomaly detection, model drift, model crisis, model competition, model revolution, paradigm change, and then we're back to normal science. Let me briefly talk about what this means in Kuhn's argument and how the sunspot cycle stuff fits in. Okay, we can think of the lack of a broad unit of consensus. We didn't have an idea about sunspots before Schwabe took notes on them. His log of observations and the inference of a 10-year cycle still didn't give us a theory. It didn't give us some consensus about our understanding. But once Wolf created this big catalog of data, give scientists a big body of data, and what happens? They're going to get their calculators out and start calculating and start figuring some things out, they feel like, on the data. So we've got this given, sunspots are given as they've been for millennia. They're going to follow a sine wave and so on and so on. And there's a key element, that the assumption that the scientific community knows what the world is like. When we in universities train students, just like we hams Elmer beginning hams, we do a similar thing. Go read the fundamental books, go read the fundamental ideas, i.e. we know what the world is like in this regard, and here's what we should do. This is called puzzle solving. We're not changing the world, we're solving one little puzzle. So predicting a sunspot cycle based solely upon past solar cycle behavior as an 11-year period, which we've been doing it over and over and over again. And some of the people like Lucian Schwabe and some others have said so. But when these anomalies occur, we can't really figure these things out. As Eric Nichols said, what happens? The scientific world resists this. No, you just didn't do it right. No, it works like that. Ever built a dipole and it didn't work, and you went and asked some of the gurus in your club, and you took a formula and you measured and went, oh, you didn't do it right. We know how that works. I'm not questioning how to build a dipole, mind you. I'm not saying that. I'm just giving you an example. So when these anomalies occur, to kind of get into the boundary maintenance mode, top experts still can't agree, but we're sticking with the paradigm. Well, what if those anomalies build up? The model tends to drift. In that formula for a dipole, what is the number, Nick, for it goes in the numerator? It's 468. Well, that's not really the number, is it? That's in the real world, but not the number in free space, right? Oh, you were talking about free space. Now I get it. So if the model drift occurs enough so that there's these other things going on, then people begin to wonder, and they don't shout so loudly of the virtues of the existing paradigm. McIntosh and his team submitted to Science magazine 10 years ago in 2012, a paper that most of their current ideas that they're publishing were in that paper. I've read it. I read that 2 years ago. It was rejected. Why? Boundary maintenance of the existing paradigm. But when those anomalies get sufficient attention by scientists who get outside the boundaries of that paradigm, then the model is in crisis because it can be split. Once McIntosh's team published some data, they finally had a breakthrough and published one little paper. Once that little paper's out there, then people read it and they go, he's saying something different. What are they doing? I better read on that because they may be onto something. So once the NASA NOAA team put their predictions out and McIntosh put theirs out, then the horse race has begun. We've got model competition. We've got the NASA NOAA model, and then we've got the McIntosh team. The NASA NOAA model doesn't tell you how they got their numbers. McIntosh tells you explicitly, and they show you their data. So you have these competing paradigms, and with one offers a model that, and this is important, more consistent with instrumental observations at the core of the science. What would that be? They can predict sunspots better than NASA NOAA. Moreover, it tells you why. Have a greater theoretical precision. Now, I think this is where we are. I think we are here in this process. We got model competition going. Now, if it holds up, there'll be a shift of adherence from the old paradigm. And does that happen by old graybeards like me and others sit around? Oh, I say, I was in the middle of an apricot flambe when it occurred that Macintosh might be right. No, it happens like rats from a sinking ship. They abandon the old paradigm and very quickly come to a new one. Okay, there's a little nutshell thought on Kuhn. What is this new paradigm? It's a theory to explain some characterizations of a sunspot cycle. Now, Macintosh began to delve more seriously about what causes sunspots. And he recognized what you saw in that film about the dominance of magnetic aspects of the sun and their dynamo actions. If those of you who are old enough to reflect this, no, this is not a 1970s orange shag carpet from your fraternity party house that got danced on a lot, okay? No, that's not what that is. That is the closest picture to date that we have of the sun. And what looks like shag carpet are the filaments that are being swirled like what hair I have remaining. If I went out in the wind here, the picture behind me is actually out my office door. It's a reservoir that we live on. And sometimes it's windy. And so it's, you know, it's like magnetics moving filaments around on the sun. Over here on the right, we have a model. This is not an observation, but it's a model of magnetic lines that have been estimated, some from the core and some from the surface. Remember in the video, the magnetic forces stop some of the filaments at the surface, causing a sunspot. So here's a brief snippet of this new paradigm. We present a new observational paradigm. They didn't stick their head in the sun. It's observational. They illustrate the production, and that's a causal word, the production of the approximate 11-year sunspot cycle. It captures the features of the 22-year magnetic activity cycle. And so the sunspot cycle is encompassed in this longer by a factor of 2. It's something that functions within the magnetic cycle. There are temporally overlapping bands in the magnetic cycle that shape and form the 2 of the 11-year sunspot cycles. And it's this realization that magnetic flux, see the previous shag carpet picture, associated with these deep-rooted tubes that emerge in a coherent fashion. So they're arguing that these tubes in the sun, by virtue of the dynamo, somehow operate in a coherent way. Remember my 2 magnets when I couldn't push them together? Imagine a tube of those magnets and something going through them that had an opposing force. It may glide very gently. Those of you who have been in the computer world for a long time may remember a device called a Bernoulli box. It was a box that had disk about twice the thickness and twice the length of my Apple iPad. Using the mathematician Bernoulli's principles about pressure, air pressure, which is similar to the magnetic flux argument, it could make the disk spin very, very stably, and hence we could record computer data on it. So that's what they were talking about back in 2012. So the reviewers blocked it, said no, bah humbug. It was a challenging start, but they persisted. Now, I want to point this out to you. I gave this talk to another group, the HAMSci group that I'm a scientist on, and Ward Silver in N0AX with ARL was there, and he didn't have an answer to this. Back in the 1940 issue of the ARL handbook on page 319, I noticed a phrase I found quite odd. 11 or 22-year sunspot activity cycles. Wow. Well, you're going to see how that might have occurred by virtue of what was going on right before 1940. So let's look at this idea that Macintosh and his team have. The sunspot cycle that we know and love if it's working well. And here's the 22-year-old magneto cycle named after George Hale. red versus blue or polarities, like I demonstrated with the two Earth magnets. And notice what happens over time. This is the latitude of the sun, 0 to 90 degrees in each hemisphere. So over time, these magnetic fields, they tend to go toward the equator, but they flip right at the bottom or the trough of each embedded 11-year solar cycle. They overlap for a period of time, just like me trying to put the magnets together. Imagine a bunch of magnets. I don't have enough hands to try to do that. And then up here and here, we have the polarity flip, where one dominates and it flips. Okay. So here are some key bullet points. The 11-year sunspot cycle is actually influenced substantially by the 22-year magnetic cycle of the Hale magnetic cycle. Hale was like Schwabe. He observed some things and developed an idea about a regularly occurring pattern. He was wrong about one part of it, and that was the flipping part. But the modulation of the sun, according to McIntosh, is a direct result of the interaction with those overlapping bands of the fundamental Hale cycle. Magnetic flux, deep-rooted magnetic tubes. They have, remember what the guy in the video said, these polar convective recycling time. He was already talking about that. So how does one sunspot cycle go to another? Well, there's an event, and Scott, if anything, has a great sense of humor. He named it after Arnold Schwarzenegger's character of the Terminator. So the Terminator events happen. I'm going to demonstrate that to you in a little bit. Happen, and this replaces the solar minimum and solar maximum that we tend to use. It's the difference between Terminator to Terminator that is our sunspot cycle. When that happens, there's a tsunami of magnetic activity that occurs, and the Terminator is just a different way of looking at it. So here's the real punchline for us. We want to know what? One of the hams in our discussion before we started recording was, how good is cycle 25 going to be? NOAA NASA says not so good. Well, McIntosh says because they're not using the right predictor of what causes it. The length of time between one Terminator and the next Terminator shapes how high the next sunspot cycle is going to reach. Let's look at that pretty carefully. First, here's George Hale. Now, he worked at the Wilson Observatory near Los Angeles. Look at this picture for a second. That's not fundamentally different from what you saw at the Kitt Peak Observatory in Arizona, is it? There's a reason. After Los Angeles got so much smog, they had to move out of LA and then moved to Arizona. So this activity was moved from Wilson Observatory to Kitt Peak. So what he did in this marvelous little paper, if you ever want to visit back in time, scientists laid it all out there. They didn't hide their weaknesses as much as they do today. He connected the northern and southern hemisphere magnetic bands that you saw previously, and they have opposite polarization. They flipped around the minimum observed sunspot numbers and reversed again at the next solar minimum. His work is legend in solar physics. So what the argument by McIntosh and this group is, here's a segment of this Hale cycle, and here's some panels that correspond with the period in the upper panel. So you've got this magnetic band as they're moving. You see the tail end here moving to the equator. It's just march to the equator when it flips polarization here to here and here down to here. You see this begin to happen, and they hypothesize that there are these magnetic flux tubes internally that help this occur. And then once the sunspot minimum has occurred, boom, there's a tsunami of activity, and we're going to see a simulation in a slide or two that causes a torsional rotation of how this works. My little demonstration can't do justice to everything going on inside the sun as a dynamo. So look at the dashed lines. This is one Terminator event, and here's the next Terminator event. And notice this is our popular SFI, or solar flux index. Solar flux index connected to the sunspot cycle by a mathematical relationship. So the black line is overall sunspots. The red and blue lines are separate counts by hemisphere. And these are actually observed bright points that astrophysicists observe that actually tell us about the Hale cycle. These bright points are indicators, and they're called a butterfly diagram. And you can see what, because they look like the wings of a butterfly. And you can see this over there. So what's a terminator happen? You see this terminator, it ends, then boom, there's a rush back up to about 30 or to 55 degrees. I'm putting you to sleep, Russell. I apologize. And then you see it, what happens again? This repeats itself. So we've been in an illusion, just like a magician says, don't look at this hand while I'm getting your wallet with the other. We've been looking only at the sunspots, and their team is saying, yes, but also look at the man behind the curtain when the Shakespeare play is going on. There's also stuff going on with the Hale cycle. All right, now this dynamo, this is Dick Potty et al., one of McIntosh's colleagues. Notice this is the equator. As you move back out, now we're going to start over. Okay, now they've got to the equator, and what's happening? Magnetism is shaking out, and there's a tsunami rushing to the poles. And look at what happens when the white lines come up. This is like a covey of quail that's been disturbed, and they flutter up. I once fired a shotgun 3 times when I stepped on a covey of quail. I somehow think this is not unlike that, because all of a sudden, within a 27-day solar rotation, this tsunami of activity can kick off the new sunspot cycle, and suddenly the sunspots have reappeared, and we're into another cycle. Now, here's another way of looking at this, and it's an animated graphic, and you'll see where these two magnetic bands are, and you'll see this moving at the same time. This is synchronized. You'll see where the sunspots are, and you'll see this magnetic bands. We'll watch it a couple of times just to get a feel for this. You'll see now equator, boom, it kicks off. Boom, that tsunami rushes back. Boom, boom, it hits again. We'll play it one more time. So you see when it gets to the equator, then it flips, and there's a tsunami of magnetic activity, and then the next sunspot cycle kicks off. Now you'll see some things differ, because you'll see that there's an asymmetry in each hemisphere sometimes. And I've been asked this, and I don't know the answer. But well, what if this hemisphere is different? Is this why you have these jagged peaks? Perhaps. Remember I said I wasn't a solar physicist? I don't know, but when I get a chance to chat directly with Scott, I'm going to ask him. But here's the animation of the synchronization of the 22-year magnetic cycle with our 2 11-year cycles, and how that works. Okay, I just got this morning. This is in a paper that's yet to be accepted for publication. They are actually getting what are called synoptic observations of this toroidal magnetic field. Think a real version of this characterization here, where they're directly observing these magnetic bands, and you get a little more detail and how they move to the equator and then flip. They're getting closer and closer, folks. They're getting closer and closer. When this is published, there'll be another nail in the coffin of the existing paradigm. I truly believe that. Well, I want to go back to something I didn't mention. Notice what this does not explain. This one's this high, this one's that high, this one's this high. Well, it's kind of close, and then it goes back up. We haven't explained what determines the amplitude. Well, it's that difference between one terminator and another. Let's look at this diagram. Where's cycle 24? It's right here. Now, this is the official NOAA NASA predictions. It's about the same, 125 sunspots, something like that. So yeah, 25, it's going to be about like 24, no big deal. Carl Schwabe said, yeah, it's going to be low, followed by some low ones. Well, look at what the difference between Terminator 1 and Terminator 2 was in years. For cycle 24, it was about 13 years. Well, what was the delta for cycle 25? Cycle 25, it was a little over 9 years. So here's the punchline. This box right here, the shorter the delta, the time period between terminators, the stronger or higher the next sunspot's amplitude is going to be. The shorter the distance, the higher. Well, is there pent-up magnetic energy? Gosh, I don't know. However, this was a key publication in 2020. I had the privilege of reading that ahead of time. And I said, Scott, look, you've got the idea and you've got the data, and the data for 25 is beginning to work. It's beginning to be more accurate. And we'll see how accurate here in a second. But that's what predicts the next amplitude. Bob Lehman, another colleague at Maryland, he's come out more recently with a solar clock where we got solar minimum, solar maximum, the pre-terminator and the terminator, and different kinds of solar flares. So they've created a solar clock where we'll predict after the tsunami occurs, boom, we're going to have just a flurry of sunspots. So in the future, I predict, instead of that solar terrestrial widget, that I've got on my website, and we tend to see them all over, we may have a version of this that tracks this in an ongoing basis to track where we are in the cycle of sunspots. Okay, here are their projections based upon that previous model. NASA NOAA is actually a little, what we call in statistics, platykurtic, after the bill of a platypus, whereas the Macintosh team has a higher peak, and yet it drops off more sharply. Clearly two distinctly different projections. In the second article in RadCom, we published for the first time the solar flux index projection. I may toy around with getting these data on a spreadsheet from Bob Lehman and lay the contest over this one, and then get the previous cycle's solar flux index and do contest to contest and see how did things work. It might be fun, might be a waste of time. We'll see. All right. So in this timing terminators paper that Lehman had published, and I just showed you, they came up with a different method to define terminators. They had been using the complex bright points data sets, which are large, they're raster based. And as my friend Joe Barry, who's a GIS guru in Colorado, said back in the 80s, as I was getting into GIS, raster data are faster, but vector data are corrector data. So they've got some formulas using a Hilbert phase of the sunspot number and the solar flux index to predict with more accuracy the historical terminator timing. I've encouraged them, go back in time and get all the terminators that you can and show how much more accurate they are than previous. I want to mention this Hilbert phase. This is a real good example. Their biggest criticism were primarily from people with an engineering background. It says, Hilbert, you need to use fast Fourier. Well, fast Fourier doesn't look at the phase angle of the sunspot number, and that's what needed to be. Remember that, give a small boy a hammer and everything's a nail. So this is part of the boundary maintenance things that can happen. But they've got now, the key question that Carl Lucius Schwabe emailed me, says, Frank, when are you going to be able to, and of course I'm not, but when is Macintosh going to be able to predict the bloody Terminator? Well, they've got a method to do so now. So here's their official versus Macintosh comparison. And when you look at this, I took this off this morning. This is the latest chart at a website, Helio Forecast, and there's a guy who's tracking this. And so you've got the actual sunspots. Last month, it was exactly on the prediction. Well, it dropped this month as it did the month before. Does that mean it's going to continue to go down like this? Not in the history of sunspot cycles back to 1750, it's not. Now, if it does something different, hey, we'll learn something. But look at the difference between the NASA NOAA predictions, the Macintosh team predictions, and what we're actually observing. Are we not in crisis? Which one would you bet on? If you went to a doctor because you thought you might have cancer, and that doctor had a bad track record of predicting, and another one had a model that could predict it, what seems to be much more accurately, whose hands would you put your life in? Well, I've been in those shoes. I know which one I chose, and I happen to be here today because I went with the person who had the better track record. And that's not the same thing as sunspots, I will grant you. But at what point will you stop believing the official predictions and begin believing this other model? Remember in that Kuhnian diagram, I said, we are here. A lot of it's about acceptance and belief. And the question that I raise here, and I'll end the talk with this, are we on the cusp of a scientific revolution in sunspot models? Well, scientific philosophy, teleology need not apply. That's not a scientific theory. New peer-reviewed theory construction, Macintosh and his team are undergoing peer review. They're publishing it in scientific magazines. They're not just putting some numbers out there and saying, hey, we're not going to tell you how we did them, but this is what we came up with. And that's kind of what Nathan Cohen, W1YW did. Here's a photocopy of the last one. This is what the next one's going to be. And they've got empirical models. And I think when you put all these together, I think we are on the cusp of a scientific revolution. Now let's go back. Let's go back to the future, to quote a movie. Back to 1919 in London. A century ago, the world waited for some sailing ships to come back to London. They had taken out astronomers to Brazil and the island of Principe to take some photo plates of a solar eclipse that was going to happen. This young whippersnapper, Albert Einstein, had a sub-theorem of his theory of relativity, I think published in 1914, that light would bend. Well, gosh, how can you test that? Well, this eclipse, if we get these two different locations, we can see the light bending. Here you go. Here's Newton. Newton reigns. Here's the young whippersnapper, some guy from Switzerland at latest stop, who was a patent clerk. He doesn't hold a professorial chair at Cambridge. Who is this pipsqueak? So they challenged each other. And so these expeditions that the British Royal Society and the Royal Astronomical Society funded, they went and the literate world awaited. Well, once they got back, this was the headline of the Times of London on November 7th, 1919. Revolution in science, new theory of the universe, Newtonian ideas overthrown. And as I put in RadCom, who now reads Newton for science rather than history? So will we follow the NASA NOAA predictions in the future if this stays on par and accurate? I don't know, but it can be the case. Some paradigms don't work out. There was a famous book by Gary Taubes called Bad Science. You remember something called cold fusion from the state of Utah? Gosh, it violated the third order of thermodynamics. It made more energy than it was put in. And no, that didn't happen. That was more of a farce than anything. They don't always work out, but will this one? Will we be on the cusp of a scientific revolution in our understanding and forecasting of the sunspot cycle? You can follow along at helioforecast.space. Every month, the data are updated, and McIntosh and his team have put their reputations and their science out there for everybody to see. They put their reputations on the line. They just want to find out the answer. And so do I. And I hope you do too. So thanks for listening. I know it's been long and it's been a little bit of a tedious path here for us, but I'm going to leave it there. Nick, if you can wake up a few of them and see if they've got any questions, I'm more than happy to entertain them.
Frank, that was really interesting and very good indeed. And I think a lot of food for thought in both your presentation and, of course, the work by McIntosh and his team that are working on the work that he's doing. And the fantastic thing, of course, is for those of us in the room here tonight, that over the next 2 or 3 years, we will find the answer out to who is on the right side of that question you are posing there about the potential for a scientific revolution and an overturning of a.
One thing that's exciting, Nick, we don't see many scientific revolutions every day. I mean, it's sign rare, and that's why I picked up on England around 1920 and Einstein. We all now know, as you talked about early on before we started with the passing of the Queen, and look at how things changed since she was initially became the monarch. Well, look at Einstein, Newton now. Who now reads Newton? Will it be the same? I don't know, but we don't see this every day.
Yeah, so my question, Frank, at the beginning of this, of course, as radio amateurs, we are all deeply fascinated in sunspots and the effect that they have on the ionosphere and how far our radio waves disappear around this planet. I think you made the observations before I open up to questions, Frank, that these sunspots are absolutely huge, aren't they? I think the average size is the size of our planet. There are smaller ones and larger ones, but they are absolutely massive. And that just the concept is very difficult for us to grasp, isn't it?
It is. I think Tabitha Scove, at least here in the States, does a great job in trying to bring some of those points from her solar physics. And she's a licensed ham, because she now kind of knows what hams think about and tries to bring that. And just the idea that even with the little magnet, one of the reasons I decided to give a little live demo, just a snippet. Look at the orders of magnitude. Just everything in the sun is so much bigger than anything we can see with our eyes. And when we get a sunspot that's coming around as we are moving around the sun and we see it on the disk, when you say it's 3 times the size of the Earth, wow.
Yes, I mean that exactly. Wow, it's the idea that and we are talking about predictions, aren't we, of sunspots at the maximum. McIntosh is talking about, anything between 150 and 300 sunspots, and each of those sunspots are on average the size of our planet. It's both hard to grasp but awe-inspiring at the same time. Frank, I'm going to chuck it out to questions to everyone else. I'm pretty sure that I'm just going to drop you a slide. I'm pretty sure everyone is there. Russell, go on, you go first.
Hi, thanks. Thanks, Frank. Very interesting talk. In one of your slides, around about 41, 42, something like that, you showed that the Macintosh prediction was perhaps showing that this cycle 25 is also going to be a short cycle. Presumably that implies that cycle 26 is going to be a very good one as well. I don't know if that's what was actually shown on that or not, or perhaps I was asleep. I'm not sure.
Let me get to that, and if I can, let me share my screen just so everyone is
Sure.
Is on that page. Okay, is this it?
Yeah.
Yeah. And I made the note, and again, as a statistician, we always look at shapes of data. And I mentioned that this is the purple one's more platokurtic. It's a little flatter in the tails. And this is a little sharper. Now, one thing to keep in mind, Russell, based on your question, and we have to take our blinders off a little bit. I'm taking my glasses off here. Take our blinders off in that just because the sunspot observations may go down a little shorter, what's the key driving force? It will be the distance from one terminator to the next. And what we don't yet understand, Russell, we have more of like Schwabe just observing the sine wave. We're at the observational stage. Even though Dick Potty created this simulation of a tsunami, it can be as short as 27 days, but it may be longer. And so one of the things that dampened, remember his initial projections were even higher. Well,
Yeah.
but he said, I'm waiting on the Terminator. Well, nobody kind of knew what is that? I mean, that's a movie, right? It's a movie character, right? And so the Terminator took longer to occur than they initially thought. So coming back to your question, it could be that 26 will be, wow, even better because there's a steep descent. But it will depend upon that tsunami and the length of time it takes for the next Terminator occur. Because remember, distance from Terminator to Terminator, what they call delta, the difference in the Terminators, will shape 26. So I think the answer is to your question, maybe.
Okay.
Assuming the red one is perfectly accurate.
Yeah.
Maybe.
The red one there also shows a fairly symmetrical graph, whereas the reality seems to be that there's a longer tail off than on the rising edge. But yeah,
it is. But now let me hasten. And Carl Schwabe sent me a note after a talk for Hamsite. I got grants as a professor to buy big computers like walk-in size freezers, if you're in that world, a Sun 690 multiprocessor, to do data visualization. So I used to help develop some of that in my field. We are looking and talking about smooth numbers here. The green ones, whereas the black is the smoothed, and then so these ones that jump around a lot are what influence our propagation. Those that are solid influence how we look at them. And so keep in mind that even though he's got this prediction, there's going to be these things jumping around all over.
Sure.
And so, but on the smoothed average, your point asks a great question. It will depend though on when this next Terminator occurs. And this last time, they had to revise their prediction because they said we'll revise it when the Terminator occurs. And it was back in December of this last year. They kept waiting. He and I were on Twitter, private messages, every day, it's coming. It's not quite there. It's like waiting for a baby. Not quite. Go boil some water, you husband. Get out of the way. So it's going to depend on when that Terminator hits, Russell. But you raise a great question.
Thank you very much, Frank.
Brilliant. Thanks, Russell. Anyone else with a question or observation to Frank? Yeah, Roger.
Yeah, hi, Frank. First of all, let me echo Nick and Russell's comment. That was clear, eloquent, and entertaining. So well done for that. Thank you. It was really interesting. I have two questions, really, or two comments. One, has anybody applied any chaos theory to this? Because you use the word cusp, and that's used a lot in chaos theory. And the second question is, has anybody betting against you? Has anybody made a wager against you yet, for fun or for real?
Well, you know, I don't play on the team Manchester United. I'm just one of the cheerleaders on the sideline. So I want to make sure I don't want to take credit for it. Let me answer this. There's two things there. One was chaos theory. Ward Silver raised this last week. Now, when Jim Gleick's book, Chaos Theory, the popular book, came out, it was all the rage. The butterfly in West Africa fluttering its wings and tornadoes in Kansas. Great stuff. Have you seen many chaos models in practice and in use? There's a few, but they're not that many. And you know why? When we have models like that, let's go back to school for a little bit. If it said, calculate the average, well, everybody could do it. Right? Why? Because it's an algebraic solution. You add up the data and you see how many, you get that number. How many data points do you have? You divide by that and you've got a number. And its accuracy is just how many digits does your calculator have? And how many digits of accuracy do the numbers have? There are solutions to models that don't operate that way. They do not have an algebraic solution where you can calculate it out. No matter how many supercomputers you have, it's not an algebraic solution. Chaos theory is one of those, or falls into that. So what you have is a model that says, okay, we have to solve so many parameters in the model, okay? You have to first see if the data that you have has enough observations so that there are unique answers to those parameters. Sometimes we put so many parameters in a model that the data can't estimate it because it doesn't have what mathematicians will call the property of identification. You can identify a singular answer for those parameters, okay? So that's the second thing you have to do. With chaos theory, you tend to want to put a lot of stuff in that kitchen sink when you're making dinner. I mean, you're putting a lot of ingredients in there. So do you have the data to actually estimate the model? And then the third thing, so how does the model get started? You say, let's just make up some answers. And then let's just compare it to the data. So you have start values. And it goes through an iterative cycle, okay? And then you have, and I won't get too much into weeds, but you have an information index for the particular model. And it says, okay, this is reasonable, that's reasonable. Okay, all right, that's reasonable, this is reasonable. Okay, we're going now. Well, the model doesn't change much and it gets on out here and it's just not changing. So we must have a good answer. And that is a way of estimating a model that is used in a bunch of areas. Econometrics is one, and some others in physics is some others, and biology is some others, and in chaos theory as well. You know, one of the challenges of chaos theory is the starting values. Because if you get a weird starting values, you can reach what's called a local minima. It gets stuck. And you can get answers that are not possible in the real world. They aren't possible to get. So that's a challenge for chaos theory. That's not saying chaos models aren't any good, but it's like that weird Japanese torque screwdriver that you need to repair that one part, and you order it and you use it every 5 years. There's just a limited number of applications. So here's what I would come back to you with that. NASA NOAA's already got 61 different models. Do we need 62 without a theory? Now that's what I want to underscore. If there is a theory about how the sun works with sunspot cycles and these other things, that lend themselves to being estimated by a chaos model, I'm all for it. And I think Macintosh would be too. But throwing just another model on the funeral pyre of 60 or more without a theory to articulate why that model will describe the sun's behavior may be fun, but are you really making more science? Anyway, that's my observation. I'm not saying chaos theory is bad. It's like that little Torx tool. You use it when it fits the situation.
What about the bets?
Oh, the bets. Hey, you want to bet? I had a guy, look, and I don't think he'd mind me using his name, Jim Heath, W6LG. He has a YouTube channel called Your Ham Radio Elmer. He's an elderly guy, you know, like me. He used to have an antenna company. He gave a talk and he went, well, that diagram, it may not work. And I said, well, but for it to fail now with the Macintosh projections, for it to drop off and just go down or go back where NASA NOAA's projections are, it would have to be unique in our observed data series back to 1750. Well, it could happen. And I said, okay, I'll bet with you. And I'll throw this out. I'll throw this out to anybody on the call. I'll bet 100 pounds. But I'm going to take the position that the sun's going to come up tomorrow. And you're going to take the opposite. Oh, but it could happen. It could happen. And even if you subscribe to Pastor Thomas Bayes and his theorems about Bayesian ideas of probability, I don't think anybody on this call is going to take the bet on the opposite side because you don't believe it. So yes, the Macintosh projections, speaking as a statistician, they could drop down, but they're not going to drop down enough given what we've already observed of this cycle. This cycle is just, it would be unique in the history of our observed record, I think. So not many bets. I mean, people can bet, but if anybody here wants to throw up a wager, put up your coppers and I'll see if I can afford to bet with you. I'm going to bet on the Macintosh team.
I tell you what, Nick, you need to get Frank back in about 8 or 9 years.
I hope I'm here, Russell, and I hope
So.
I hope to be. And I think Macintosh, even if they're wrong, they've laid a theory out here, and that's a fundamental advance just in and of itself. And I think the empirics will work themselves out, and they may have to fine tune the model. That happens. I've had to do that in a lot of my work. But yeah, it will in the pub. It will get you. You're down walking the dog with a Newcastle. It may get you fired up over putting a wager.
Thanks, Frank. Thank you. Great.
Yeah.
Anyone else with a question or observation to Frank?
Yeah.
Stuart.
I feel like I'm maybe cheating a bit here because I actually have a PhD in solar physics, but and
I don't, by the way. So
I've also forgotten most of it. How much understanding is there in terms of the actual physical processes that are driving the Hale cycle that trigger these Terminator events? Because otherwise, isn't this actually just, aren't you doing the same thing we just did with the sunspot cycle over the last few hundred years, but now with the magnetic cycle instead, in that you've taken observations of it? And
I could not ask for a better question. That is a great question. And I want to go to a slide here and go back. Now, here is a slide. I'm sorry, tell me your name again.
Stuart.
Stuart. Here's a slide that I think I'm safe in saying there is some theory that makes sense. I know that's really technical, right? Stuart, there's some theory that makes sense about these magnetic flux tubes. Okay. I think there's some agreement that these exist. Now, I think there's conjecture that they exist in this way and that they coordinate. There's conjecture. However, I don't think there's much conjecture that this pattern in the Hale cycle exists. I mean, even going back to George Ellery Hale's initial paper, we can improve on those measurements. And I think clearly it has been. Remember, I showed you this. I just got this morning, and I can't give you a great explanation about their synoptic observations. I will by tomorrow, because I'll have read this 50-page paper by tomorrow. However, with that asterisk, they're getting closer to measuring the Hale cycle than maybe ever before. And this itself is simply a simulation, sometimes taken as truth in the gospel by the public. But as you and I both know, and others, this is our best guess as to what's happening with the tsunami. So let's go back to this one. This slide, with the exception of the upper portion, is a conjecture of how these things work. Now, even with the Parker probe, I mean, we're not going to prove these or disprove these. So I think without a doubt, there's clearly some stuff that is conjecture. Let me say this. I taught a course called Structural Equation Modelings with Latent Variables for about 20 years. And we measured unobserved things like human self-concept, how you feel about yourself, other things like that, unobserved variables. I had a student ask me one time, says, Dr. Howell, I got a question. Where have the absurd variables? You've been talking for 3 hours about unobserved variables. I gather you don't like them very much. He was reading absurd rather than observed. So I used to teach that. And very often when you have these theoretical models, Stuart, you have these intervening steps and you must make assumptions. And if that model seems to work, it defines, explains, it has some prediction capability, and explains the relationship between one set of phenomena taken as exogenous or given and another set of phenomena taken as dependent or endogenous, then you work out, okay, let's see what we can detect about these intervening stages. So yeah, this isn't a new way to do science, but your point is more than well taken. Whether it's just new wine in the same bottle, as you kind of intimated, is this just not the Hale cycle revisited? Well, we're measuring the Hale cycle a lot better, I think. So I'm not sure. I mean, that's just my best take as someone who doesn't have a PhD in physics, but who's studied at the feet of Macintosh for about 2 years. That's my best shot at it. Your thoughts?
Yeah, I think there's fundamentally, I don't think there's an accepted model of how any of the magnetism found in the sun is generated at all. So I know that there's not, we don't have a functioning model of how any of the sun's magnetic field is generated. So we don't know how it changes over time either. But I think certainly it's very interesting to be able, even just being able to more accurately predict surface activity in sunspots and stuff is obviously massively beneficial, even if we don't still have a detailed physical model of how the whole system works.
Well, and from my reading of particularly dynamo theory and others, I'm reading it from an educated layperson's perspective who's read an awful lot of science. And as a statistician, over the years, I may have been called in on things like integrated pest management. Are we putting pesticides here, there, and yonder and running pests from one field and farms to another? If we integrate them, it's like a big apartment building infested with cockroaches. If only one apartment at the time sprays for the cockroaches, they just go from apartment to apartment. I've been called in to look at investigations there, EPA. So I've looked at a lot of sciences. And so from looking at this, models are always based on assumptions. And that's the first place I go, Stuart. When I read about a new model, I really go, what are their assumptions? And that's the same reason that when I read a manuscript, I read the abstract. I don't read the paper. I go to the citations. I want to see who they've cited. Then I read the paper, because then I've got an idea of where they're coming from. So I couldn't agree with you more. And I think you sort of zoned in on probably one of the weakest parts. And then I think if Scott were here, and I invited him to come, but he's also an administrator at his research institute. He's in charge of all the airplanes and their flying sensors and doing all kinds of things. So he's got a lot of administrative duties as well. I think if he were here, he would say, yes, you've raised a great question. This is what we think is happening with this convective system with the magnetic tubes. Not everybody agrees with that, but again, he's laying it out there for peer review, and NOAA, NASA's not. So that'd be the only argument, Stuart, for the. I'll show you mine. You show me yours.
Yeah. I mean, definitely the utility of the prediction is not. It looks like it's going to be very useful. What year was the NOAA NASA model predictions published?
Well, they released the last one, I think, in 2019. If you don't get RadCom and don't have the paper, just pop me an email. I'm good on QRZ. I tell you what I will do. I will make sure Nick has them. I don't think Elaine would be upset with me circulating them to those of you here. She sees it as good advertising for RadCom and for the society, so there's no problem. The full citation is there, complete with a URL link. I won't try to do it from memory because it's a weird URL. They will not tell you anything. I wrote her for just higher resolution graphics than what you saw in my PowerPoint. Nothing, crickets. They won't communicate. But it was 2019 when they released them.
It's just worth noting that the 2022 Macintosh paper had 2 or 3 years on them in terms of predicting the. But
the only update though, now keep in mind, Stuart, the only update that Macintosh team has had, they're not doing what we call in statistics a step ahead forecast. In other words, let's say you run a grocery store and you got milk flow. Okay, here's my milk demand for next month, but based on it, so they're not doing that. They did it one time, and they said they were going to do it when they could nail down when the Terminator occurred, because again, the delta is the key predictor. So they aren't updating and this stuff goes.
Thank you. It was very interesting talk.
Thank you.
Brilliant. Lovely. Thank you, Stuart. Anyone else with a question to Frank? Yeah, Richard. Yeah, Richard, you're on mute.
Hello, Frank. You mentioned that black holes were due to magnetic field being so strong and it stops the light coming out of the sun.
That's what the guy at NASA said. Yeah, that was in the video I showed you. Yeah.
Right.
Maybe he's very sad.
Well, I don't know that they're the black holes that astronomers tend to talk about out in space. They are simply dark spots on the sun that are created by magnetic forces that stop the filaments from leaving. I think that's what he was getting at. So
they appear dark because they're significantly colder than sun.
I assume, and yet I don't think any astronomer alive would stick his head in that cooler spot. But maybe one day we can figure out how to send a probe sensor into one of them, and maybe we'll learn more. The Parker probe may tell us some. It's kind of hard to convince the public, hey, we want to shoot this missile at the sun because we'll learn stuff about it. People don't ordinarily grasp why is that important.
You wouldn't get that close.
Well, but one of the key things, and Scott has said this, kind of the Rosetta Stone to the solar system is understanding our sun. And the more we can understand about our sun, the more we know about the role of our planet in our solar system and how different stars are likely to work. So if we don't stick our head in the sand in terms of solar travel, we kind of need to know some of this stuff as best we can. So the notion that that's a Rosetta Stone to all stars and perhaps life and all that is certainly something that the Cornell astronomer Carl Sagan, when he talked about the billions and billions of stars out there.
You see, what you mentioned about magnetic fields, and people say that black holes are gravitational forces. Does that mean that, or could it be that black spots are very dense pieces of areas or volumes in the sun?
I can't answer that. I just don't have the science.
You see, the problem is with that, once a black hole starts, it just gets bigger and bigger.
But see, I think you're making an incorrect connection. I think you plugged a wire in the wrong port. I don't think because he said it was dark that it's a black hole in the definition of antimatter in space. I don't think that's the case. He's talking about what our sensors observe on the sun that we call sunspots. They happen to be dark, but every dark spot is not equivalent to a black hole. I mean, that would be the way I would interpret it, but you know.
Yeah, that's Richard. I think Stuart was making that point as well. They're dark because they're cooler. I mean, we're looking at
all relative.
Stuart, correct me if I'm wrong, but I think you're looking at something like 1,000 degrees Celsius difference between the dark spot area and the surrounding part of the sun. You know, you're looking at the difference between 6,500 degrees and 5,500 degrees, that kind of nature of things. That's a very different phenomena from that of you know, the concept that you're describing in space, which is a different thing altogether.
It's a little like the confusion in the term ohms of resistance and ohms of impedance. They are different phenomena, yet for whatever reason, we use a metric that uses the same word. So black hole in space with antimatter and all that good stuff versus a black spot on the sun sounds alike, but as Nick said, I think they're fundamentally a different phenomena.
Yeah, no, that's fair enough. It's within a certain range and it's all relative.
Yeah.
No, it's fair enough.
Okay, thank you, Richard. Anyone else with a question to Frank? Yeah, Frank. I mean, before you go and before we wind this up, I think you started off with an observation which is critical for us radio amateurs. That, you know, when we're looking at this sine wave of whether we're comparing the NASA NOAA prediction to Scott's prediction or any others, we've got to be very careful with these smooth sunspot numbers, because the ones that we are as radio amateurs very interested in are the actual sunspot numbers. And I think if you go back to one of the diagrams you were showing of the cycles, even at the much better cycles we had in the 70s and 80s, solar cycle 21 and solar cycle 22, which are still higher than the prediction for solar cycle 25 under Scott McIntosh's prediction. Even within those smooth figures, there are these peaks of huge sunspots, absolutely massive numbers of sunspots for over several days, which obviously for us coincided with those days when we can be running 5 watts on 10 meters into a quarter wave antenna and be speaking to a guy in Hawaii as if he's next door to us.
Or someone could be running an illegal CB radio in the U.S. with a 5-element Yagi and talking to someone in Medellin, Colombia every day at noon. Now, I don't know anybody that may have done that, But you're exactly right. Nick, I will say this, and I wish I had the data. I might try to pull it up. I really think, when we look at the aging problem in amateur radio, a lot of us graybeards, part of that we call the baby boomers in the U.S. If you look at it, when the baby boom was young, what happened? We had that magnificent solar cycle. Incredible. So maybe cycle 25 will be something that will encourage some younger blokes today, boys and girls, because of what you just said, that, with a cheap radio, so to speak, you can work the world. But the other thing, and I've gotten this question, is if the sunspots are so good, why can't I make a contact? And this is a corollary of your point, Nick, and that I started off with. Well, let's remember, sunspots are an input to a process of a number of things that allow us to complete a transmit-receive circuit. One of the things that I'm trying to do is to take with HamSci is to take the corpus of the Whisper database, which is now about 12 years. So it's a complete sunspot cycle, and to try to link the transmission and the reception and link things like sunspots, SFI, solar flares, and some other sort of macro phenomenon to see how they predict the link in specific locations at specific times. And where you are in the gray line, and it's a lot of data to it. I haven't gotten that completed, but that's part of something that I have on my agenda, because it links some of this stuff like how the sun behaves to our hand on our dial as we began talking about the Kenwood TS590. You kind of go from hand on the VFO and looking the SDR. So that's some stuff we need to do. And we need to remember, sunspots aren't everything. They may be an overall governor of how fast our car will go, but it's not necessarily mean how well our car will operate or that sort of thing. So still a lot of work to be done, even if Macintosh is spot on. There's still a lot for us to understand to predict whether we will get an opening to where we want to talk or communicate in one way or another.
Yeah, which is what makes amateur radio such great fun, doesn't it?
Yeah,
Frank, I'd like to thank you so much for coming tonight. Can we show appreciation to Frank for his contributions tonight? It's absolutely excellent. Well done.
Thank you. Thank you very much. I've always enjoyed meeting with you, and I hope that one day you're going to get back in Pie Hall and enjoy the pie and peas. And so one day if I get to visit your country, I'd love to come see you. So maybe that will happen. So look, I will send Nick the PDFs, and if you need it, don't have it, just pop Nick a note, and he can forward you the two articles. And if you want to communicate with me, I'm good on QRZ anytime.
See you.